So I don't know, is there any hand raised already? If not, I have a couple of questions already.
There's no raised hand right now.
Okay, let's start with the fun part.
So just a quick reminder, if you have a question, just raise your hand and then you can speak. So
okay,
Cruz,
Johanna,
please go on.
Let's start with you. I think it's the easier one. I mean, I have a clear picture of what we wanted to do on the front. And I just wanted to point out one of the key points. When you make the number of parameters, okay, we have the 15 booleans parameters. Then we have 25 float parameters that are the technical parameters for each one of the technology. So there is like 40 parameters. Those cannot be avoided. But then they have 700,000 parameters for the time steps. This is a huge amount of parameters that we can avoid putting a control there. A control, I mean, even if you go to a deep learning model, that I will not suggest doing that. I mean, deep learning models don't go that big. You know, I mean, usually are much smaller. So we have a huge amount of potential improvement there, because a typical control have, I don't know, 100, 200, 1,000 parameters. If you go crazy with a neural network with a lot of deep neural network, I mean, not so big deep neural network. So I mean, there is a lot of place where we can put there, remove this thing. I mean, the need to look for this kind of hourly and go that way. But this is a one possibility. The other possibility is to make an hybrid algorithm. When we took, let's say, we took out the integer part, let's say the 1-0 part, this go to the evolutionary algorithm that is good for doing this kind of assessment, and then we just put the linear part in the other one. And we know now that this is a linear problem. It's not an integer linear problem. This is a linear problem because we know this is a 0 or a 1 or a particular combination of 0 or 1. So this is now a linear problem that we can solve quick, very fast, and we just reduce the amount of variables that are there, because there is not going to be a vector of entire ones. There is going to be just a couple of them. So there is going to be like very small linear programming that we know that those could be solved relatively fast. So we can explore, let's say, the kind of sub-problems quite fast, looking for the good solution, the good combination of solution. So this is kind of an interesting hybrid algorithm for that could work quite well. Okay. This is for one point. And the other one is that we can try to do other kind of, I mean, putting the control there. I mean, to just remove the 7,000 parameters out, put in there a function in a genetic programming way. I don't know, we can put an STRLM program, a fuzzy logic, a neural network, I don't know. We could discuss later on what is the best point to put there a control and try to optimize the control. And now we have two results. We have the optimization, but we have also the control. And the control is important because it's a result. It's an actual thing that we can even try to discuss if we can be patented or whatever we can think on the topic. Okay, this is an actual result. But the other place is that we have this explainability of the results. And even more, from my point of view, this is more realistic because I'm not sure if it will be feasible to deploy a control strategy that solve a linear integral programming in each one of the houses of an entire Europe. But putting a microcontroller that has, I don't know, a fuzzy logic control, this is what they do actually nowadays. So this is not something that it will be more realistic model of the entire Europe that trying to solve from above, let's say in a macro scale, the entire the solution. So I think those are good points in order to try to go this route. Okay. Later on, we can see if we hit or face the evolutionary problem and we don't see anything and the convergence is crap and, well, all this nasty thing that we have with evolutionary algorithm, or we don't found the right combination of parameters and the hyperparameters, we cannot choose them. Well, there is a lot of crap there, but I think that we have at least a list of actions that we can do it and we can test and trying to go there. Johanna, I don't know if you wanted to say something.
I'm just understanding what you're saying. I think the second approach you mentioned, that you use a genetic algorithm to generate the zeros and ones and then go in a linear programming, I understand, and I think it really makes sense because of time. So you would have a genetic algorithm which generates zeros and ones, and then you optimize the size of the device and the energy flows.
Yeah, so we are in the easy problem for you that you have said. This is easy.
Yes, I mean we will have to do it a lot of times, because then I think there is, yeah, you make the 0 ones, then you optimize, then you evaluate the fitness, then you go back to the 0 ones. So this will be a lot of iterations. And
but you can catch it. You can catch the results. That this is a good point. You don't repeat the calculation every time. I mean, if you know that this particular vector have this solution, you know that this is. Normally you don't repeat too much, but it could happen. And well, yeah, if we have, I mean, the problems are going to be smaller and linear, so you can go fast. So you can do a lot of them.
yes, so I totally agree that this is a good idea in general. And with the control, I'm more and more understanding what you're aiming to do. But still, I mean, you have the genetic algorithm which chooses 0 or 1 plus the capacity.
Exactly.
Plus the control strategy.
Exactly. But
and then you evaluate the result.
Exactly. But the key point is that those are 3 different blocks that could operate separately. Mm-hmm. So we have a convolutionary process, let's say. One is the zeros and ones, as we have before. Then we have another one that is the optimization of the actual parameters. And then we have a third one that is the control. So we don't have 2 blocks as we have shown before, but we have 3 blocks. So it's more difficult, the back and forward on the 3 blocks, and it's going to be more difficult to implement, but you mean we are going to reduce the size of the problem dramatically. I mean, if depending on the control that we put there, we can start with simple controls with, I don't know, 10, 20 parameters. So we are ending in a problem with less than 100 parameters that are easily solvable. Okay. And then we can increase the complexity of the control if we need it. And the key point is that we can put whatever we want it in the control. I mean, we can put whatever we think of. I mean, we can even put a forecasting algorithm inside the control and it's not make any problem at all. I mean, so we can build or optimize a very absurdly complex control there and test inside the whole framework easily. Easily. I mean, but this is something that I think that we should try to do I don't know. While we do the other thing, I mean, let's try to go back and forward and try to carry it out.
Bruce? About the parameters, a lot of control parameters usually depend on the system. If we have to optimize the control for every system, that's going to take a lot of time, won't it? Because then you end up with a couple of hundred simulations for every generation of the main system parameters. Or are you envisioning that we are using relative things like, for example, for a control strategy for the battery, you need to have the set points, when to charge and discharge and all these things.
No, but you just need to, I mean, you need to, for the control parameter has to decide, I mean, what you are changing is to an optimization problem by a simulation problem. So you just put the control and you run 1 year and simulate 1 year. It's, I mean, because they don't need to optimize anything. We just need to calculate, iterate over a function several times. So it's quite fast and quite easy. And what you just need to do is, okay, I tune the couple of parameters. I don't know, the battery is going to have some inputs, the status of the battery, the PV production, the energy consumption. I don't know, we can put even forecasting, I mean, the forecasting energy consumption and the forecasting energy consumption. I don't know, I don't know, perhaps the battery is going to have 6 parameters, the control strategy. And then we just put the model and develop this model, okay? If we can even put there some initial, let's say, control handmade, let's say. So we provide the algorithm to a jump start, let's say, like a control that is already hand-tuned, and see if they can improve it. We have done that in the past, and they have been able to tune a handmade model and increase the performance while not creating absurd controls. I mean, absurd in the sense that you take a look to the thing. I mean, you can see what the control is doing. I mean, the decision that they make, but they are so messy and not messy, not ordered. I mean, that is complex to follow up what it's doing. But if you provide a jump start with a right, let's say, a good, I mean, a handmade control, they can improve it and tune it, and you continue to be able to check what it's doing because you found the original structure some way. So it's easier to track. But I completely agree that this is, I mean, the size of the control is going to be big, but it's not going to be in the hundreds of thousands parameters. So it's going to be smaller, and this is a good thing.
What is still a problem for me is that all the things are connected. So I think that's similar to what Noah said before. So for example, if I have one solution from the genetic algorithm with a battery and a certain capacity, and then I choose a control strategy, and in the next iteration I don't have a battery anymore, then everything is changing. The control has to be for, I mean, the control has to be a structure for the full thing, and it's going to take as an input parameter the vector of zeros and ones to turn off or on several parts of the control. I mean, the control is not going to be easy. I mean, it's going to be quite complex, and it's going to be quite interesting feel of I mean, depending if we go for something that is interpretable, because if we go for a neural network, we are going to have an inputs and outputs, and they will do their stuff internally, and we don't know what is going to, I mean, what is the instruction. And it's going to be always the same size, always the same, I mean, it's going to be more predictable, let's say, on size, but we lose the interpretability of the control. But, I mean, this is the kind of thing that we need to leverage later on when we enter to this kind of problems. But I mean, as I was always saying, there is no silver bullet here. I mean, if you get something, you are going to lose something.
So we cannot have everything. So we need to think and take into consideration what Thomas has said, for example, that is the interpretability of the results. If we can gain a very good control, but we cannot interpret the results, if we are going to do that, we are to be very sure that the control is good. So yeah, this is the kind of thing. Okay, I don't want it to monopolize the session. I don't know if there is more question. I have a lot of more questions. So.
I have one too.
Okay, Johanna, go.
I'm just wondering if we are, for example, using the genetic algorithm to generate the decision variables. Is there any way to evaluate the fitness without going into the linear programming part?
No. You're going to need to go to the other part. I mean, this is the graph that they put there. When we put the arrow that way, do you remember that we have some rounds, and then we have a arrow that way, and then we have bullets, points in the other place? It's because we transfer solution from one place to the other. So we need to evaluate the entire problem normally, usually, okay? There is some cases where you can split and calculate half of the fitness or something like that, and then you can combine them, and there is another, this is another kind of co-evolutionary strategies, but usually you need the full problem to evaluate the fitness function. It's a pity, but I mean, what you are gaining is that you can focus on part, you can cache things, and well.
Thanks.
Okay, any question from the audience? Okay, no, Axel?
No.
Okay, go next one. I have a lot of questions now for Noah. Let's start for the easiest one. How have you created the household IDs? I mean, you just put a household, 1, 0, a 10, and that's it.
Just randomly.
But households has a geographical meaning or characteristic or something like that?
No. The meaning comes from the people in the household.
Okay, so you just wanted to have.
I wanted to combine the people into households that fit all the statistics and that are reasonably put together.
Yeah. So your fitness function, it's the similarity with the aggregation statistics, let's say.
Yes, and additionally common sense stuff.
Yeah. Okay. Okay. Now my second question was about the fitness function, but I think that now I have to think more carefully to this problem, because it's quite different to what I normally do. I mean, several things that we will try is to, if you know that you have the very clever idea first is to create first the population of people and then to mix them into houses. I think this is okay. This is the way to go. But now I think that you can do a little bit better, because you know that you wanted at the end 100 normal families, let's say 10 gay couples and 1,000, I don't know, single families or single person in a house, no, or something like that. So instead of creating the buildings at random, I will create already the buildings with the labels. So I will create, if you know that you have to create 100 houses, I will create that way. But the main problem,
The thing is, I don't know exactly it's 100. I know it's about 100 because one statistic for the average families might be like, here should be 90 families of this size, and the other one says the average family size should be that. And they contradict each other because they're from two different years and bullshit like that. So you can't pre-create because all of them might be slightly off.
Okay. Okay. So now I understand a little bit better the problem.
There's not a single reliable number that you can actually say, this is what I believe in. But all of them should be approximately correct.
So you are testing more or less how many of the criteria or the statistic criteria are good or not. I mean, and your fitness function was if you fulfill or not fulfill each one of the criteria, or how much do you fulfill or not? How close are you to each criteria?
How close with an R squared?
Okay, good.
Because otherwise it wouldn't converge at all.
Exactly. This is what is going to happen.
And then the hard factors get weighted a little bit more. I think it was factor 10 or something. And the soft stuff is ×1.
Okay.
Because I don't care if there's a couple of more or less gay couples.
Yeah, it's just, yeah. I think that this is quite, I mean, you have made a quite good approach. What I don't really like, let's say, or sounds strange to me is the bit, I mean, because for me, when you do the bit representation, I mean, and you go that deep, is because the bit representation have some semantic meaning. But I don't found the semantic meaning of the representation, because you are not, I mean, there is no relation between the bit representation, let's say, and the household type or the person type or whatever. So why don't use just a number? Because if you put a number, I mean, your length is the same, but your number of parameters are less. Because you can use integral values, so it's the same. I mean, you are using integral value, but your evolutionary algorithm are easier to use and probably carry out more semantic meaning. This could works or this could not works. I mean, Noah.
But if I use integers, then I need to limit the integers, right? The reason why I use bits to represent the numbers was because with the 10 bits, I get a minimum solution space, the shortest possible genome. That still makes sense. If I use integers, I have 32 bits per person.
But you don't care. You are going to have just one value. You are going to have one parameter. I mean, what the key point is not the length of your genome. I mean, you don't need to think on the genome on the number of bits. It's the number of parameters. So if you have a float as a parameter, it's scaled of 1. If you see the float expansion, then you have a lot of parameters. But do you really need to operate over the float expansion, or do you need to operate over the float, over the number? This is the key point. And as far as I understood your problem, that I need to think more and more and more, I mean, I don't see a reason on why do you need to have to operate over the integral expansion, let's say, the bit expansion of the number. I think that you can consider just a person, I mean, have just one parameter, that is a building, the identification of the building.
Yeah.
So you have one parameter per person. The bit expansion is the same. I mean, you are not going to, I mean, the bit length of your solution is the same, but you are reducing drastically the number of parameters. It's something similar to what quantum computer seems to be doing, no? I mean, they summarize a float, I mean, a lot of floats in just one parameter. So this is the kind of thing that you could do it. But I'm not sure if this is going to work. I mean, because I'm not sure if I completely understand all the structure and all the constraints there. But this is one point that we can check later on. Okay, two things that I don't know if you have tried. The first one is the main problem that you are seeing is convergence. So if you increase the number of people, you don't converge to a solution.
Yeah.
Even if you put absolutely number of
well, it's very slow.
iteration.
It still converges eventually, but it's not like for the small problem.
Okay.
I didn't try running it for a couple of days and see what happens. Probably it still converges eventually, but not at the useful speed.
What the key point, well, you need to check also with other alternatives to see if you converge or not in the same time. And this is also a good point, because all problems have, all algorithms have problem when you increase the size. And the key point is what is worse when you go up. The key point here is that evolutionary algorithms are absolutely easy to parallelize. I mean, and you know it. So, and you have access to absolutely large computer. So this is a potential solution, but this is not going to, I mean, if you have convergence problem, parallelize is not going to solve them. What is going to solve it is it's going to convert faster, but it's not going to solve the other problem. If you have problem with the convergence, what you can try to do is to split the problem in sub-problems, and then trying to solve each one independently with smaller, smaller population that you know it converge, and then try to plug into the entire problem. As you have already advanced a lot in the search field, you are not going to have, I mean, you are going to explore a different part of the solution space, and probably you are going to converge and to go a little bit deeper. I mean, and you can find good solutions. And you can even try to do co-evolutionary process when you have population that migrate and these kind of things, but it's a little bit more complex and lose the key point, no? That the algorithms are simple, that you can program it. You don't need to use any different library that you can use or not use. I mean, this kind of thing. So those are things that you can try as well. I don't know if you think it's worth the time. Okay. Is there any more question from the audience? Is everyone is quite silent?
Yeah, there's no question from the audience yet.
So Noah, Johanna, you wanted to comment on something?
I would be very interested in how the control algorithm is programmed to be optimizable.
Control.
Yeah.
I mean, the hyperparameters.
You just use a normal control algorithm and make all the parameters as. Or how? Or do you optimize the code itself too?
No, I mean, the easiest way to do that, I mean, we have a colleague that is now doing a fuzzy logic controller. The fuzzy logic controller this is an example, I mean, there is other examples. The fuzzy logic controller, I don't know if you are familiar, you have this fuzzy logic, I mean, the linguistic part, when you have this if and else there, and then you have the numerical part when you put more, you control the shape, no, or the fuzzy part, no, or where are the triangles and this type of thing. So this is a perfect place to put a co-evolutionary algorithm, because one part of the algorithm is working with the linguistic part, taking care of zeros or ones if you wanted to see it, but I mean, you can go to the text and see what is the closest that are in the if parts. I mean, and you check one and others. And there is a co-evolutionary run that it's optimizing the constants. Is someone talking? No. Okay. So you can optimize the control that way. Okay. But this is with fuzzy logic. I mean, you can put just a neural network there with input parameters. I don't know, the status of the battery. I mean, every control parameter that you wanted to say, and as output, any controllable parameters. I mean, actuator parameters, and let the neural network do their business. I mean,
do you have experience with that already?
Yes.
How many generations do you need? How much computational time until something like that converges?
We have controlled. I will say chemical reaction. It was olefins to, I don't remember the exact thing. And we have 3 controller parameters. And one thing that we can control, that was the temperature, I think. No, we have 3. I mean, the 3 things are inputs and outputs. So, I mean, it was the same thing, the inputs and the outputs. Traditional controls just put set points. I mean, the control temperature is this one, the amount of water is that amount, and I don't remember the other one. And those are fixed at the start. The process goes in continuous mode until the catalytic is destroyed. So what you put into the generation and regeneration of the catalytic process and blah, blah, blah. This is the traditional way. And we put a neural network there that control the 3 of them dynamically in order to avoid the deactivation of the catalytics. And we have, I don't know, I think we have double in simulation. We have double the yield of the system in simulation.
Yeah.
Because, and we can do that over a normal computer. I mean, no fancy HPC system or anything like that. I mean,
yeah. But for my for yearly simulation, I'm about at 1 minute per year, maybe 2 or 3 if I use the more sophisticated thermal storage models and things like that. So if every individual basically needs 2 to 3 minutes. So how many generations? How big does the population need to be until then the control algorithm?
We cheat.
Okay.
I'm going to explain how we cheat there. We have something similar to what you are saying. I mean, our finite function evaluation, if we go to the full model, that was solve a set of differential equation, partial differential equation, and all this fancy stuff. It was like a couple of minutes also per individual. Okay. So what we have done is to have a very short population. I think it was like 10 models, 10 control models only. And we have also a surrogate model of the chemical reaction made by neural networks that works like in milliseconds. I mean, it was like 1,000 of time faster than the other one. We have even implemented our own neural network class because it was like 40,000 faster than the one provided by the MATLAB or something like that, because at the end, a neural network evaluation is just a matrix multiplication. So we just take in the coefficients and make the actual multiplication without all the blowout that they made. So at the end, it was absurdly fast because we just need to check the actual solution with the actual let's say, differential equation. I mean, the numerical solver, just every 10, I will say, every 10 generation, and only with the LET. So we make a lot of cheats and work quite well. I mean, the solution, when we found the solution, we say, okay, the solution has sense. And when we check the final finite function is over with the actual model. I mean, and we can spend a couple of minutes there. and it was a very good yield. I mean, we provided. I was remembering that we have parallelized the algorithm, and we ran in a computer with 10 cores or something like that. So I mean, every generation it was fitted to one generation per core, one individual per core. So we go fast. I mean, it's like we run the other way, and it takes a couple of days or something like that in computation. That is feasible. I mean,
Okay.
and you have access to absolutely large computers, so you can increase your population.
Yeah, but still, I mean, we will need to run that a couple of times, right, to get proper control algorithms.
Probably. I mean, this is a high risk, high gain. I mean, yeah. For sure. I mean, it could work. I mean, if the control that it's needed is simple enough. I mean, good controls are simple. We are going to find it easily. Let's say, if the control that you need is complex. I mean, complex in the sense that they need very large interrelationship between things, and the chains of if and else, or the length of the neural network are very big, then it's going to be more difficult. But I don't know, perhaps I mean, not very good controls but they're not too complex are there, and we need to look for them or not. But unless we start looking for them, we don't know.
Yeah.
We know that we have 70,000 parameters.
Well,
700,000 parameters. So.
Well, the control strategy for a multi-energy system is usually about between 100 and 500 lines of code, because you have the different modes depending on what types you have in there, and then you have depending on how the PV is right now and what the forecast is and all these things. So that's already quite a lot of involved parameters and code.
But the key problem is the number of, I mean, for neural networks, the length is prefixed at the start. So it's more or less you can control the complexity. For the other ones, you need to control the complexity. And I know how to do that. I mean, because I mean, one of my PhD thesis was about that, how to control the complexity of the control. I mean, of the control there. So I mean, I know how to do that, and it's worked quite well. But yeah, I think that we definitely have to try that. I mean, and to check.
How well can you use neural networks if you have a lot of different completely different modes where things are operating completely differently?
They are going to, I mean, the main problem could be if you have at the end, let's say, constraints that this has not to be, this input parameter have to be 0, if this one has to be 1 or something like that. If you have complex constraints there, you need to impose to the neural network, and the neural network have to learn them because it's dumb. And this could be the main problem. But if there is not too much complexity on there, I mean, the only thing that is an input parameter that is 0, 2, or 1. I mean, and the network was okay. This is going to be 0, and he's going to it's going to be propagated, and here is a 0. This output is going to be a 0. Okay, this is going to be easily learned. The main problem is that if this is a 0 and this is a 1 and this is a 2 and blah, then this could be a 0, and and this is hard constraint.
Yeah, and in reality, it's like that.
Yeah, I know. But let's see if we have a big enough neural network, it could find these kind of things. But let's see. I mean, the key point is that for neural networks has one good thing is you don't need to think too much about the structure of the neural network. You just know what are the inputs and the outputs, and you need to know that. I mean, and you just put the biggest neural network that you can afford, let's say, with your computational power, and hit the button and wait and pray. And if you get good results, or if you don't get good results, you start thinking a little bit about how we can improve a little bit the structure and the inputs and output on examples and these type of things. But if not, I mean, you can even get very good results with this approach. That is the non-brain approach, let's say.
Mm.
Well, there is another things. I mean, if you wanted interpretability, then we need to go to Fusilogics, and then things get a little bit more complex, but not too much complex. We need to put the linguistic and this kind of things, but I mean, we can optimize things there. I mean, and I know how to work on that. But let's see. Let's see. Okay, I don't know if anything more questions.
No.
Axel,
No,
no more questions.
no more questions. No more raised.
No,
hands.
Johanna, more question. The rest of the audience.
I think
No.
it's pretty silent.
So this is going to be like the weddings. Talk now or or forever or never again.
Yeah, if you have no further points,
No, I think we can close here.
then we will keep it short. Yes.
Yes. Yeah.
Yeah. Thank you to you all